Remember Dr. Sharma?
Alright, folks. I have to admit, I'm not quite sure what time it is. My watch is broken. It's a little off, but anyway, let's go ahead and get started. For one of you left this in my my office? Oh, Love's? Here, these are yours? Yeah, okay. Wasn't sure. And anyway, so not a lot of class business. Got your homeworks. I'm going to work a lot of example problems, and I have a lot of example problems. I actually decided to rewrite my extra hour notes at the last moment, so I'm a little bit perturbed right now. Where are you guys? You have an exam? You're just late. Where's everyone? What do you think class attendance is right now? What'd you say, 50%? 51%. 50%, that's an all-time low. Well, I don't know, I don't like that too much. I feel like people are using the videos as substitutes. I don't exactly want that. Quiz?
Attendance quiz.
Oh, quiz? You know what I could do is I could just come up with something like a derivation and just write it down right now. You guys just pull out a sheet of paper and just turn them in. Yeah.
All right.
No, let's do it. Well, I mean, it sounds like 3 points. In all honesty, maybe I'll just do that if I have a sheet from you. I can be very generous, right? Come on, folks. Seriously, all right. If we do this, it's your fault. I just want you to remember that. Do you want to do it? Yeah. That's overall yes. Okay. Sorry, folks. I'm going to write up on the board, so I'm going to turn off the camera. Sorry if you're not here. So that was the quiz. So thank you for turning them in. Just put them over here when you're done at the end of the day. Sorry, guys. I told you this would happen. So don't rub it in their nose when you see them next, I bet Monday. I bet we're going to double our attendance. So congrats. Again, I'm going to be extremely generous on the extra points. If you didn't quite get the question, that's fine. I'm probably just going to give you full credit. So, I'm sorry, I am feeling especially mean because if you didn't check the news, Spock just died. Spock. You people have no culture. Who's Spock? Leonard Nimoy, not the young Spock, the old Spock. He had pulmonary obstructions, which you folks don't know. Pulmonary means lung. That ends up getting a lot of people, including my grandma. So. Anyway, all right, everyone, come on, let's get going. We've already wasted enough time on our little jokes. So, let's review last time. And again, I'm going to be a little bit funky today. I just didn't get a lot of chance to review my notes before class because I decided to rewrite my notes right before class. And God knows we just lost 10 minutes for the quiz. Again, review what we did last time. We went over how G changed with T. And just to remind you, since we can't figure out how G changes with T, we had to do G over T. And that was minus H over, let's talk about changes in G. So this is the delta G of a reaction. And that's minus delta H of the reaction over T squared. Okay, it's a little odd, but basically the important thing is this tells us whether the change of gives energy of an actual chemical reaction. We're going to get to actual chemical reactions on Monday. It tells you whether, if your reaction isn't going well, do you want to heat the reaction or cool it? And then you start over at that lower or higher constant temperature. So remember, I can still think about changing temperature, even for an equation of energy that's all about maintaining temperature. It actually still makes sense. So I hope that doesn't get you too cross-eyed. I mean, it's pretty simple, right? So we talked about that. And for reasons I'll get into, I can talk a little bit more about how you actually calculate delta G in the next hour. It's actually terribly important. I don't think I emphasize this enough. It's terribly important when you're adiabatic or isothermal because you can't actually calculate delta G or delta H for adiabatic conditions easily. I'm never going to ask it because you really can't do it. You need like a computer. So I'll talk about that next time. Then we talk about entropy and how entropies of materials are, here I should just add the term. So this is, if this something is a gas, P over T, okay, and then the next thing is a plasma, so I'm not going to worry about that. So what this allows engineers to do is to take all the chemicals that exist that we care about, which is probably a couple million, and calculate the entropy. And of course, we're going to calculate entropy at standard temperature, 25 degrees C, and put them in giant tables in the back of your book, like the giant table in the back of your book. And as I mentioned before, this gives me the absolute S, the absolute entropy of a material. And if I wanted to, I can also calculate the absolute G, which is one I ultimately am going to really care about practically, but I could do A too, because that's kind of important in power plants. H and U are rarely useful because I don't have entropy regulators, right? If I really want this reaction to go, I really don't care about U or H. Now, notice that in the back of the book, you have S written at standard state, that's 1 bar pressure and 25. See, I'm talking about this Monday, by the way, I'm just a preview, right? You know, to hear things more and more, it gets easier. So I see in the back of the book, the table in the back of the book, I've got entropy, but I don't have G or H. I've got delta G, delta H. That's the formation gives energy. That's the formation enthalpy. So that's not the same as the absolute G, the absolute H. They're not the same thing. And that's because we had to know entropy, and I'll explain that more in the next hour. You must know the absolute entropy of gasoline, of oxygen to react the two. You need that number, but you don't need the absolute G. You don't need the absolute H. You can actually figure all that stuff out relative from other conditions, and I'm getting to that Monday. So just again to preview that, that's why you see entropy as entropy in the table, but not G. Instead, it's delta formation Gs. And that actually comes from the first law. Energy can't be created or destroyed. But entropy is unfortunately much more complicated than that. I don't have that for for entropy, any kind of first law like that. Now remember that the Nernst theorem simply said it gave me the starting point, and that means I can calculate the absolute entropy, and that's why I feel like entropy is real. So the third law I think just proves the second law. And then, okay, then what else did I talk about? I talked a little bit about how heat capacity is related to entropy. I mean, obviously, CPdT is the change in heat, so this is the change in heat over temperature, which is the definition of entropy, so that's sensible. And then I told you a little bit about how this changes with temperature up to room temperature. And if you are doing a reaction off room temperature, you have to calculate a new S, and you do it wherever you're at here. And you have this 1 over T, proportional to T sub 3 vaporized, which led to quantum mechanics, and I explained a little bit about that. You get these jumps, just boom, and then it tends to rise like this, and then so now something's melted, and then it vaporized. It just goes up and up and up and up and up. And again, I said a little bit about how this part led to the discovery of quantum mechanics, just because. Now metals, so this is not metals. Again, to help you out a little bit with what's coming up, metals are actually linear. Metals. Okay, and that's linear. Proportional to T. Sorry, my board work again. I didn't prepare enough for today. Sorry about that. So metals are a little different. I just want to point that out. And again, it's a quantum mechanical thing. This one's kind of neat. So I'm just going to go over some random factoids about entropy, and then we're going to get away from a gas expands, a gas contracts. So metals do this because of a diagram that you're going to see in 346. And that is, I guess this would be internal energy. And we have these ways of describing how electrons fill electronic states. So I have a slab of iron. It has energy levels where the electrons occupy those energy levels. Only one electron per state. But spin up, spin down is considered different. So technically we have 2 electrons in every state. But since their spin is different. This is population. So again, this is something you're going to see in 346. I want you to be used to it. It's just one lecture that you're going to see this stuff. So what happens is, I lost my notes, but I think I know this stuff. Based on a finite temperature, these are energy levels, and so I should draw a bunch of lines, but the lines are so dense, there's so many lines in a solid material, that I really don't draw it that way. I draw it like as bands. And here's the population. Looks like this. And this point here is called a Fermi level. Fermi level. It's just a word we use. It's really what we're getting into today is the chemical potential of an electron. If I'm going to take an electron from outer space and toss it into this metal, which is fine, that's not hard, that's how much energy it would take. Actually, it's how much energy would be released. Metals love to eat electrons. It releases energy. It's happy to have that electron. And that means that if I'm going to, that means energy would have been released. That means the bar is hot. So again, electrons will just soak up, metal bar will soak up electrons like no one's business. Now here's the thing. Now again, remember, heat capacity are related to degrees of freedom, and we talked about that last time. These electrons have a degree of freedom. They can occupy higher energy states by using a little thermal energy. So these little electrons in all these states, like this guy here, it doesn't take much to give him a little, with the temperature, I give it a little bit of a pop to a higher state. And, sorry, I should say plus T. Little heat, so the bar is very cold, and I warm it up. And as I warm it up, I see the heat capacity is linear. That's because these electrons are just kind of using that thermal energy to jump to higher energy levels. It doesn't take any effort. It just takes kT of energy. kT is linear. Right, so this is a degree of freedom for the material that other things don't have. So it's a factoid. Anyway, you'll see it next semester, just to get you more used to all this quantum stuff. All right, here's another thing, and then I'm done with entropy. I am not going to bring this up again, by the way, so you can zone out completely. Prefer it if you didn't, but this is on some standard exams, especially if, God forbid, you actually want to be a chemist. And, okay, there's 2 things. One is Troughton's rule. Troughton's rule. You will never see this again from me. I'm bored to death with this. That is that the vaporization entropy, the change in vaporization entropy per mole. Sorry, I just should have an SMM. Too soon. Seriously, Anastasia Steele. What was the other guy's name? 16th grade? God, Jesus Christ. Anyway. Yeah, that sounds very realistic. Still too soon. Vaporization per mole. The TVAP is almost always 85 joules per k mole. remember that joules per K is entropy, but this is the per molar entropy. And so I do that with this. We're going to see a lot more of this per molar stuff. And again, I'm at constant pressure where H is now heat. And I'm going to be sticking at constant pressure and temperature from now a long time. And it's almost always 85 joules per K. And that's because the entropy, remember this is the entropy of the liquid minus the gas, or the solid minus the gas for like CO2, because that's what it does. Liquids and gases have very low entropies. So the entropy is mostly that of the gas. And gases have very similar entropies because they're gases. And that's where that motion through space is most of where their entropy is. Yeah, they still have degrees of freedom, and that means that's why some things have higher entropy than others, if they're gases. So it just comes out that because of the general commonality in gas entropy and the low entropy of a solid or liquid, this is almost always 85. Whatever. You'll never see this again. Not from me. But I have seen it on tests. Okay, here's another little concept I utterly don't care about, but must teach. Wow, I have a really great attitude. And that is residual entropy. Residual entropy. I was just looking at, the reason I'm going to go over this stuff is that I was recently looking at the ACS Standardized Physical Chemistry exam. If you go to grad school and you want to become a physical chemist, you have to take this test pretty much at every university. It's just to make sure that you have some idea what you're doing. And I saw this on the exam. So if you go to grad school in physical chemistry, this will be on the exam. So I'm going to go over it, but there's not really a lot to it. And what happens is that it's often portrayed, residual entropy is portrayed as the third law failing. So the entropy of some things at 0 degrees is not 0. And we can measure that, so it's hard to describe. So that sounds like the third law. Remember, a perfect crystal at 0 K has 0 entropy, joules per K entropy. And this says, no, some things actually do have some entropy even when they're very cold. The answer is you can't perfectly crystallize everything. So this is no perfect crystal. And again, this is a practical thing. It doesn't mean the third law is wrong. Just like how some books, some textbooks say that the equipartition theorem is wrong. It's correct. It's our inability to understand degrees of freedom that gets confusing, and we're just not smart enough to understand really what degrees of freedom are. The third law is fine. It's just you can't always practically build a perfect crystal. And that is in the case, the most famous case is unfortunately water. And so, of course, this is at a very low temperature. And so it's now a crystal. It's now ice. But now the dangerous thing is, this is kind of important. Water in the ice form forms these tetrahedral structure. Remember, it's got the little rabbit ears for lone pairs. And so that means that neighbor water molecules are hydrogen bonding to them. Actually, let me draw it like this. A little dash, 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 dash. So these are nearby waters that are hydrogen bonding to this thing. And then that gets confusing. You see, what happens is that hydrogen is so light. It's kind of cool to put this in your head. But what can happen is, here's the oxygen here. What it can do is lose this hydrogen, with this causing this guy to lose his hydrogen, causing another guy to lose his hydrogen, and finally we come back to the guy that shed it to begin with. In other words, these hydrogens are shuttling around. These are its bonds, but they can break, and then these can become real bonds, and the other guy who lost its hydrogen gains it from another one. It just goes on in these big circular patterns. And it's because hydrogen is so light. And so that's not a perfect crystal. If you could cool, see, the thing is you can't cool things absolutely. Again, I'm doing a lot of 346 stuff. You cannot cool to 0 degrees K, because that violates an uncertainty principle. You can't know where something is and how fast it's going. That prevents anyone from ever achieving perfect 0. If you could do it, this wouldn't happen. This shuttling of protons would not happen, but we can't do it. You can't prevent it no matter how low you go. Okay, now, what is the residual entropy? So that you get a bit of a better idea of these microstate stuff and the probability way of seeing entropy. So this isn't a change in entropy, this is entropy itself. I've got, this is a bit of a pain in the rear. Okay, so the problem is with this perfect crystal is I don't know whose protons are who. That's what it comes down to. That gives me 6 configurations that could be true or may not be true, I don't know. That's the whole point. So these could be the right hydrogens. Not draw myself into a box. These could be the hydrogens. What else? Let's see. Hopefully I won't get confused and forget. These could be the hydrogens. What else? Looks like I can go across. These could be the hydrogens. 1, 2, 3, 4, 5, and then, then the opposite of this. Sorry, this looks kind of messy. If you didn't even write this out, and just maybe absorb that would be fine. Okay, so I've got 6 ways of deciding whose hydrogens are whose. So that means that's like 6, 2, 3, 4, 5. Yeah, so I have 6 microstates. KLN6. Problem. Number entropy is KD. Natural log of the degrees of randomness or number of microstates. W is equal to 6, but not quite. You see, you've overcounted because I have used all 4 possible pairs of protons. 4 protons. Water has 2 protons. Right, so I can't say that every one of these is valid because then water has 4 protons, not 2. There's another molecule claiming at least 2 of these. So you can't say that there's actually 6. Times the overcount. Okay, now the answer is there. The answer is on the overcount that I've got 2 protons that belong to this, but there's only a 50-50 chance that proton is actually my guy's protons. So that's 1/2 on the first one times 1/2 on the second one. So entropy ends up being KD ln 6/4. Is that right? 6/4. And of course I'll have Avogadro's number. I'm going to do this with 18 mils of water, 1 mole of water. And that's R, ln 3/2, and that is 34 joules per k mole. Remember, as soon as I decided that I had a mole, as soon as I decided I was working with a mole, I was calculating the per molar entropy. That's why I have a mole in here. Okay, so anyway. The experimental value, 3.4. I thought that was too high. Experimental number is 3.5. 3.5 joules per k. And again, it's not perfect, it's awfully close, so that's pretty good. And it shows this whole way of thinking of microstates that I hope you kind of can see a little bit more about how this actually works. Although I'm not going to test you on this, because I just don't care. It's just an inability to make a perfect crystal. It's an inability to cool things to absolute low temperatures. So I don't think it's that interesting. And again, our ability to understand microstates, the difference is that it's just not perfect. This, again, isn't nature. This is us drawing pictures. Nature doesn't work by pictures, all right? So it's not fully correct. But I don't know what is fully correct because I'm just a person. So anyway, so that's residual entropy. And you can also use CO as an example, and CO is easy because it's so non-polar. You know, you do those Debye polarization stuff, and you see that CO should be polar, but it's really not for weird reasons. And so when you make a crystal, they want to line up, like this, but occasionally one is like that, and another one's like this. So you end up with RLN2. This way, that way, and that's again pretty close to the experimental. That's kind of perfect. Okay. All right, that's it. No more gases. Just kidding. We're going to come back to gases every now and then. And it's going to be on your homework. It's going to be on your second test. It will not be on your third test. It will be on the final. But now we're going to completely change gears. So if you were sick of a gas expands and gas contracts, you're going to miss it because this other stuff. This other stuff is I don't, it's a little bit harder. And I'm going to start having to make approximations. I have not. I have not made an approximation with anything I've done except maybe use the perfect gas law, which, right, okay, that's an approximation, sure, but whatever I did with it was perfect. And I can use Van der Waals equation, which is pretty accurate, but again, just a model that isn't perfect. But within those limitations, everything I've done in terms of derivations or this present homework set, which I'm going to help you on quite a bit, I have 5 pages of example derivations that are almost identical to what we have. Those are perfect derivations, and I like that. We're getting into an area where that is impossible, at least in this class. And so, anyway, that's where we're at. And what else do I want to say? Oh yeah, just to remind you, okay, I've already been blabbering about how energies are relative because of the first law. And that's why I don't look at the back of the table and see G, I see delta formation in G. And I can still use that in Hess's law calculations. Remember, you had that in freshman, right? Remember Hess's law where you take an equation and you add another, a chemical reaction, you add another chemical reaction, sometimes you flip it, sometimes you don't, and they add up to other chemical reactions. So we're going to get into that on Monday. He had it as freshman. We did it in high school too. So you can do that because energy is relative. Now here's the damnedest thing. If you're going to get A and B to react, maybe that's air and gasoline, I'm sure. If I'm going to get them to react, they have to mix together. Now, if you look closely in the back of the table in the back of the book, those formation Gs, or absolute entropies, which is a bit nicer because I like absolute numbers a little bit better than relative numbers, even though it doesn't matter. It doesn't matter. Those numbers are for pure substances, for a mole of a pure substance at standard temperature pressure. That's 1 bar and 25 degrees C. Don't write that down, we're getting there. As soon as something changes, I'm not at the right temperature pressure, which is going to be common, and you're going to figure out how to account for that. But as soon as I mix A and B together, oxygen and gasoline, those numbers are wrong. So when you were a freshman and you were given a chemical equation and you had to calculate delta G, you were wrong. In fact, you were way off because you didn't take into account that when you mix them, which you have to do to get them to react, when you mix them, you change those numbers. You just weren't told that you had done that, just to make it easy on you. So as you can see that I'm kind of frustrated at times because it's like my job to go back and fix all the mistakes. And I understand that we simplify things to make it easier and palatable, but we also simplify them to the point they were wrong. So that kind of blows. All right, open systems. And this is going to be the answer to the last question on the homework. I'm about to do it. So anyway, now what else do I want to say? All right, so we're going to start with what is an open system. I could take my magic cylinder and poke a hole in it and shove more gas in. That would be an open system. No, I'm not going to do that because that's confusing beyond words. An open system is not going to be an open beaker. I'll have my magic piston at times. But what's going to happen is what's inside of it changes. And I'm going to start with ice melting because that's real easy. That counts. That's a legitimate chemical reaction. It's kind of a stupid chemical reaction, but it does count. So we're going to start with that. So when I say an open system, it means the ice will melt. So I have something going and something coming. Now, they were in the container, and so no moles were added or subtracted, but within the microcosm of A and B, I lost some A and I got some B. And so that I will define as an open system. And we're going to do phase changes because those are the easiest chemical reactions to get. And then we're going to do actual chemical reactions. And I'm going to focus actually on gas reactions because those are easy. And I'll introduce you to how liquid and even solid, the reactions occur in the solid state. It's a whole field, it's a very minor field called solid state chemistry. And it's important for geology, obviously. And I can tell you a little bit how solid chemical reactions work. You take what's called a flux. So this is how you like to make minerals, and that's kind of important. Sometimes we need to make minerals. And you take what's called a flux, which is just like SiO2, that's fairly common. And you add chemicals into it, and you heat it up to a slag. This is actually how we make phosphorus, by the way. You take phosphates you dig out of the ground, you add it to coke, carbon, and SiO2, which is glass, and out comes white phosphorus. And that's how we make fertilizer, by the way. So anyway, okay, so there's chemical reactions in the gas phase, which is what I'm going to focus on. I will introduce chemical reactions in the liquid and solid phase as well. Anyway, I'm jumping like 3 weeks ahead of myself. Okay, here's the number one problem. That I have to redefine this thing. Not too bad. It's not too bad. I got this thing still. It looks like I haven't done anything. But remember, in the magic sealed container, something's going to go and something's going to come. And that's because there's a reaction occurring. So I have to tack on a term. I'm going to have, this is ultimately because energy is extensive. So all our state variables, A, U, H, and G, and S, they're all extensive. So if I'm going to take some ice away and add some H2O, I'm going to lose some U from my ice because it's gone, and I'll gain some U from my water because there's more of it there. So I have to tack on this term. You're going to love this, but look, there's one for all of them. Let me do A. Actually, on the homework, can you tell me, what did I, number 10, can someone tell me real quick what did I ask for that? Because I don't want to answer that question. I want to give a different example. Sorry about this. I should have double checked. See, I change my question, of course, every semester, and I don't remember which one I asked. Did I say equate G in U or A in U?
G and U.
Final question is A. It says like we and you. You want to look at it?
No, it's not. Here, sorry. I just, again, I don't want to be too cheap, and I forgot what I asked. I'm pretty embarrassed at this. Okay, so I'm going to do A. You're going to do A and U on the homework, and so I'm going to do G and U. That's good. This is actually harder. Let me do G. Sorry, I didn't remember what I put all in. Minus SDT. Okay, so you can see I'm clearly doing your homework. And so now remember, this is the definition of a change of a function. And when I'm changing a variable, I hold the other variables constant, which are natural variables, depending whether I'm talking about U, G, H, or A. Okay. So what appears to blow is that, and I can write H and an A as well, but it's kind of painful to do that, so I won't write them all down, and I don't need to, because something magical happens with this. So ostensibly, I've made it harder. You can imagine, like, oh, there's some crazy different equation for this one, and then it's a little different on that one, just like work is a little different, and heat's a little different depending on, is it 80, beta, is it, okay, at least there's one saving grace when it comes to this one. And again, this is the hard one. Okay, so let me do this. So this is how you'll do your homework, except it's a little bit easier than what I'm doing now. Minus the change in TS plus the change in PD. Okay, just to remind you of that. Now, this is going to be 10 miles 10 miles wide, by the way. All right, I'll start. Let's just add them in. I got them right here. Okay, minus SVT. I'm going to have to write a little smaller. BEP plus the change in G, expected N, and constant P and T, EN, is equal to the change in U, which I have there. That's PDS minus PDB plus the change in U with respect to N at constant S and D, EN. Okay, now I got minus TDS minus SDT. Plus PDB. Told you, PDB. Real pain in the rear. Look at all that. Okay, you're going to see where I'm going with this in a second. And I'm telling you that despite the fact I've got, seems like 4 new equations for A, H, U, and G, I really don't. Let's see here. Gone, 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 gone. What am I left with? So I don't have much I can do over here. G, N, constant PT. You can probably skip this what I'm writing right now because it's going to be very starkly apparent what I'm doing. I'm just writing the leftover terms. UVN and S and D, constant change in N. Okay. Gone, 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 gone. All right, those cancel across the board, and therefore the change in G with respect to N, constant P and T, is a change in U with respect to N, constant S and D. here's the saving grace. There aren't going to be 4 new ln VF over VIs or God knows what. There's only one because all the energies are the same. And this is chemical potential. Sorry, a little shorthand. Okay, now again, you'll do the same thing for A. You're just not going to have that term, right? So it's going to be very easy. So I just gave you the answer anyway. But I don't mind doing that. You still have to write it out. What else do I want to say? Okay, there's a couple other little factoids about this because as we get into phases, and different components, that's oxygen is a component in only octane, right? So I talk about octane content of gasoline, so octane will be gasoline. So we have different materials and we have different phases, right? Because octane will be a liquid and oxygen will be a gas. Or I'm about to do an ice cube, I have liquid water, I've got solid water. So greater than one component. Okay, now this is, I don't know, 2 liquids pouring into each other reacting. What you do is say that Eg, and we're going to be at constant T and P. So I'm going to go ahead and wipe out those first 2 terms in delta G. I'm sorry, up here. These are now gone. It just leaves me that bit. And the way you do this, and this again is this is all about symbols. So I have to be really careful in this next section about actual chemical reactions. I have to be really careful with my symbology, like vaporization and fusion. It's kind of important. I don't want to get it wrong, because that's kind of a disservice to you, especially when you take a test and I haven't done it right. So what we do is, of course, T and P are held constant. So I use the letter I, and I say that there's K components. Again, a tradition to call the number of components, that's what's reacting, the 2 things that are reacting. It's traditional to say that there's K of them. And we give them this little subscript. Okay, now, greater than one phase. So actually, I'm going to take components. If I have more than one phase, and I definitely have already got more than one component, cross phases. Okay, so if you understand, this is ethanol and water with an ice cube, right? 2 things and more than one phase. Okay, in which case I'll tack onto that. Now I've got a double sum. I'll keep this guy, the K number of components, and again that's the stuff in the vial. And then we go to Greek letters. We go to Greek letters for phases, and we say that there's R number of phases. And you know, I don't care about this stuff at all. These are ridiculous, and I'm sure in Russia they don't even have these letters because it's a Cyrillic alphabet. But I have to work with what I got. So, and those get superscripted as well. And I will try very hard to get that right. Okay, so that's how you designate components and phases. So when you see me superscripting or subscripting, that's what's happening. So look out for that. It's not a big deal. This is not something, if it's on the test, if I have you do like number 10 on the test and you don't quite get superscripts and subscripts right, I'm utterly not going to care. I think that's just trivial BS. Okay, now I'm going to do some example problems. And I'm going to have some James Bond action because I can't wait for Spectre to come out. Although I'm kind of pissed that they dropped that quantum story arc. Just like all of a sudden his girlfriend never existed. Damn bastard, why did they do that? You guys did see Casino Royale, right? So anyway, ice and water. Now, okay, yeah, ice is water, but you get my point. Liquid water. I'm just going to call it water. I can't help it. I'm going to do a lot of examples of ice and water. And so just remember that water is the liquid. And I know I'm using wrong language, but I know I'm going to say it, so I might as well just tell you I'm going to screw that up. Ice and water. Okay, now technically there's one component that's H2O, and there are two phases. And we're going to be at 0 degrees C, 1 bar of pressure. A little bit clearer, so you don't think it's an L bar, 1 bar of pressure. Okay, so now under these conditions, what's favored? Ice or water? It's a bit of a trick question. Meaning, both. Right. Kelvin just said it. Both. You're at equilibrium. Right. If you're at equilibrium. If you're at equilibrium, then delta G is what? 0. Right, 0. 0, and of course it's 50 units. I'll try to remember units, but 0. If you screw that up, maybe I'll take a point off on being a jerk, but anyway. Right now, here's the damnedest thing. Oh God, I have much time. I'll get through one of these examples. Now, some of you tell me, seriously, let's say I've got people have done this. It's really hard because to get these to an equilibrium, you have to really be careful about temperature and pressure. If you're at 0.00001 degree, you now favor liquid water. And minus 0.0001 degree, you now favor ice. So you've got to be really careful about this, but it can be done. People have done it just for the hell of it. Made perfect little refrigerators or freezers and got the conditions exactly like equilibrium. Now I drew an ice cube. I put this in, and I promise you, we're at equilibrium. I come back a week later. Do I see an ice cube? An ice cube. Now, I'm not talking about ice cube. I like him. He was famous when I was your age anyway. Do I see an ice cube? No. No, what do you see? An ice, a what?
Cylinder.
Close? Sphere. You see an ice sphere. Right, now what's happening is, you're at equilibrium, but equilibrium doesn't mean things aren't happening. Things are still happening, but they break even. So what happens is a little water freezes onto the ice, but then a little bit of ice comes back into the water. And it's going to continuously do this, but it's going to maintain itself. So it's not going to freeze over and it's not going to melt. But the cube turns into a sphere. That's actually surface energy. It's not something I've gone over, but nature abhors corners. So the ice is actually a little bit more likely to melt at corners. And then nature likes a flat surface, so some of the water will freeze to the flat surfaces. Eventually it forms a sphere because that's the minimum amount of surface area possible. It's something I really don't ever get into in this class, which is kind of bad, but there's enough stuff to talk about already. All right, so anyway, things happen. That's my point. That's very simple to understand. Okay, it's called alpha 1. Alpha 1 is ice. And alpha of 2 is water. Again, that's still liquid. Ice is still water. Now, we do ice. A little ice turns to water. Now remember, we're still at equilibrium. This is just something that still happens. And of course, yes, some water turned to ice. I wouldn't worry about that right now. Therefore, change in N1, I'm sorry, N sub I, why did I do that? Change in N1 is negative. Change in N2 is positive. Here, raise this up a bit so you can see it a little better. Okay, so that's pretty easy. Now what I'm going to do, okay, so this is chemical potential of, oh God, look at that. Sorry, superscripts, not subscripts, see? Screw it up. Yeah, sorry about that, superscripts. So chemical potential of 1, change N1, plus the chemical potential of water, change the amount of water. Now, here's the funny thing. If I lose some ice, if I lose N1 of ice, so N1 is negative, how much N do I get of water? N2? That doesn't help. Come on, think a little further. So I lose N1, and it's still, they're both H2O, so I lose a millimole of ice, I gain a mole of water. millimole. I gain a millimole of water. Okay, so the change of N2 is minus the change of N1. All right, that's very simple. You see, this is why I like this demonstration, because this is impossibly easy, but the thing is, it's general. This is still a chemical reaction. Again, it's a bad example, but what I'm going to do is correct for this, is correct for everything. So that's kind of nice. Makes understanding the stuff a lot easier. Okay, if that's the case, I got 0 joules is equal to chemical potential 1, change of N1, minus the chemical potential of water, change in N1. Right, so I just substituted this for that. Now what I've got is the chemical potential of 1 minus the chemical potential of liquid, of ice minus liquid. Okay, now, therefore, what can I get from this? Now, change in N1 may be negative, but it's not 0. It doesn't matter whether it's positive or negative. I know what it says on that. It's not matter whether it's positive or negative. Because the whole thing is 0. Therefore, I gotta make it 0. What do I do?
You're one like
Yes, right, of course. Chemical potential of the ice is equal to the chemical potential of the water. And so that means, oh God, I'm sorry, I'm not using the board too well. Again, I told you I wasn't quite prepared. So at equilibrium, chemical potentials are all equal. Okay, so there you go. And okay, let me do one more. Let's go out of equilibrium because I got the time. Please see that anyway. Then we'll break 10 minutes. Recharge the camera. So we'll get out on time. Just 1 minute. Okay. Okay. Now let's go to 1 degree C, and that's going to be at 1 bar. And in this case. Now, therefore, ice melts. Okay, the ice is melting. I've warmed it up. So, let me check my notes before I do something stupid. Okay, so ice is going to melt. So there's a change in Gibbs energy for this. Now, again, this thing's happening in the container. The container is the system. Things are happening inside the system. Just because I have 2 things in there doesn't matter. I can still say that whatever is going inside of this has a change in G. Is it positive or negative? Negative, right, of course. The ice is melting because it has to. It has to melt. That means that it's only doing that because the total change in entropy of the universe has increased as a result at a constant temperature and pressure. And so this is the total entropy times minus temperature. So that means that when this is negative, that means the total entropy change is positive. So that means it happens. Okay, in that case I've got U1 change in N1. Right, is it? Let me make sure I'm going through it. Yeah, plus. Okay, nothing is different. Next we got less than 0. And again, nothing is different. I've got U1 minus change in chemical potential of the ice. Okay, so now this guy, remember this is the amount of ice that's changing, positive or negative? It's just the same as before. The ice is melting, 1 is ice, right? It's negative. The whole thing is negative, and therefore this is positive or negative? Positive. Positive times a negative is a negative. Remember, negative win in that case. And therefore, the chemical potential of ice is greater than the chemical potential of the liquid. And the way that probably is more familiar to chemical engineers, this is mass transfer, because that's what's happening. So therefore, when you're outside of equilibrium, mass goes from high chemical potential to low chemical potential. And
remember, that's the same thing as saying that energy likes to go downhill. And this is saying the exact same thing. And the neat thing, again, is that even though I've done this for a babyish type of example, if it's true for this, it's true for everything. It's true for Gasbury. It's true for my cats when they scratch the hell out of my hand. They do every day. And so, anyway, that's that. We're actually on schedule for this class. So, 10-minute break, and I'm going to recharge the thing. Come back in 10 minutes, and we'll have questions if you have some. And then I've got lots of examples of derivations.